let's look back at that same question that we worked out in the last video. We integrated this function, all right? And we use direct line integration. Now, this time we're going to use Green's theorem. Green's theorem is usually shorter. It requires less work than line integration, all right? So what I did was to play back the video and pause it and make some screenshots of various parts, at least 2 parts, and pasted them here. I wanted to capture what we're supposed to do as well as the image of the triangle. We went around this triangle, all right? So remember, here now, Green's theorem requires that you have a closed figure. It must be continuous, all right? And you must go around it in an anti-clockwise direction. Now, here, just a few reminders. Remember, this here, is the equation which shows the vector field, all right? And then we have the horizontal component of each vector and the vertical component here of each vector, right? All right, so here now, what we really found when we did the integration, if the vector field would move an object around the triangle this way, how much work it would actually do in moving if you have to use the forces in the vector field to move the object around this path, all right? But anyway, let's use Green's theorem to deal with this. First thing, what does Green's theorem say again? Well, what Green's theorem says is that if you integrate along a curve C, where the curve forms an enclosed region of a vector field, where the horizontal component, you have a function of x and y which we call p, and this is the horizontal component of p plus. You have another function of x and y which we call q, and q is the vertical component of the vector, each vector in the vector field. This is equal to negative the double integral within the region R of the partial derivative of p with respect to y minus the partial derivative of p with respect to x dx dy, right? So here you have to remember how you do your double integral. Of course, with it in this form, you do the first integration is the entire integration you do with respect to x, and then the second one with respect to y. But of course, you could switch these around to have dy dx. So you do the dy first, and then you do the dx first. But let's see what's going on here. The function we have is the integral around a closed curve. So we have the integral of a curve around a closed boundary of 2x plus y dx. So 2x plus y dx, that is the horizontal component of each vector in the vector field, plus 3x minus 2y dy. 3x minus 2y is the vertical component in the vector field. And by the way, remember that when we complete the integration, what we have found is the amount of work done in moving an object. If the vector is a force and we move it around, remember, work is force times distance. So the answer we got here, the amount of work done would be 2 joules if you consider the vector field as applying a force to an object and it moves the object around this closed curve. So we got 2. When we did the direct line integration, we're going to see if we get 2 again when we do Green's theorem. So now we need to convert it into this form. So what we need to do is to find P. We need to find out what P is and then find the partial of P with respect to Y. Then we need to find out what Q is. Then, oh, my mistake. This should be Q. Okay. So the partial of Q with respect to X, right? So we need to find out what Q is and then find the partial of Q with respect to X. Alright? Now, here we have dx here and here. So whatever multiplies dx is P. So you can see that P is 2x plus y. Alright? So P is 2x plus y. Now we have dy here. Nice. dy is whatever multiplies. Q is whatever multiplies dy. So what is that? You see Q corresponds to 3x minus 2y. So therefore Q is equal to 3x minus 2y. Alright? And by the way, now I remember, I'm going to ask you to pause the video here and finish everything off for me. Finished? Did you get back the 2? Remember, you must practice, To properly learn math, you must do math. Right? You must practice. Alright, so here now, what happened? We need partial of P with respect to y. So the partial derivative of P with respect to y is, well, we can see that is 1. And what is the partial derivative of Q with respect to x is equal to 3. Alright? So, let's write this thing down now. We have negative double integral of partial of P with respect to y, in this case 1, minus partial of Q with respect to x is 3, and then the x dy. So this is the function here. 1 minus 3 is what? So we have negative double integral of 1 minus 3 is negative 2 dx dy. Alright. Now, this is a constant, so we could just bring it outside the integral sign and say negative negative 2. This is equal to minus negative 2 double integral of 1 dx dy. Alright. Of course, this becomes positive 2. Now what happened with the triangle here? 0, 1, 2. Alright, so let's draw the triangle here. and we set up our double integral. So this is 0, this is 1, this is 2. Okay, now you remember that the equation of this line was 2x, y equals 2x. Alright. Now, what we could do, consider that we have small elements where the width is delta x and the height is delta y. If we stack them up from the bottom here, the x-axis, upwards, they would go, well, the y, the delta, the dy would go from 0 up to 2y. So the dy would go from 0, up to 2x. And then we stack from left to right. We'll be going from 0 to 1. As we move that, we sum them up. Right? From left to right. We go from 0 to 1. Now, remember the last integral must have numbers only. Our last integral here is having a function. It's having a 2x in it. So we can switch this around. So we have 2 times the integral of from 0 to 1 dx, and the integral from 0 to 2x dy. So we do the dy first and get rid of this 2x business here. So now here we have the integral from 0 to 1, which is 0 to 2x with respect to y. This would give us what? Let's draw back the 0 to 1 and the dx, but let's deal with the first integration, the dy. This is y from 0 to 2x. Alright? So this would be 2 times the integral from 0 to 1 dx. What happened here? You substitute 2x for y first, minus, then you substitute the lower boundary 0. But when you do this, you would have 2x minus 0, which is just 2x. I wouldn't need this bracket anymore. So this is what you have. Alright? Now, you could, of course, consider rewriting this as putting this 2 outside the integral sign and multiply by that 2. So 2 2's 4, integral from 0 to 1 of x dx. Alright, so here now, this is 4 times, when you integrate this with respect to x, you have x squared over 2 from 0 to 1, which is 4 times what? Alright, so let's use, you can still use square bracket. 1 squared over 2, which is half, minus 0 squared over 2, which is 0. So it's 4 by half. Half of 4 is what? 2. So we got back the 2. The same 2 here. So you notice, once you know your double integral by regular practice, you wouldn't have any problem using Green's theorem. Alright, so that's it for now. I'll see you in the next video.